1950s with the development of the Thor Intermediate Range Ballistic Missile. Named after the Norse god of thunder, Thor was created in response to a growing fear that the Soviet Union would beat the U.S. in the deployment of a long-range ballistic missile. The goal was to design a system that could deliver a nuclear warhead to a target 2,300 miles away, the distance between the United Kingdom and Moscow. On January 25, 1957, the first Thor lifted off from the newly constructed Space Launch Complex 17 at Cape Canaveral. Following a series of early failures, the Thor team celebrated their first success on September 20, 1957. In all, 59 celebrated IRBMs were launched, with the last flight occurring in 1975. Thor began the transition from missile to space launch vehicle in 1958. On October 11, 1958, America's newly formed space agency marked its inaugural launch when Thor Able boosted NASA's Pioneer 1 on a mission to the moon, and NASA's long partnership with Thor was born. NASA and the Douglas Aircraft Company began development of the fourth and longest-lasting Thor configuration in April 1959. Using a Thor first stage and a Vanguard second and third stage, Delta I lifted off on May 13, 1960, from Cape Canaveral's Space Launch Complex 17. Though its first launch was not successful, the Delta team quickly pinpointed the failure and 3 months later delivered NASA's Echo 1 communication satellite to orbit. Following Echo 1, the Delta team racked up an impressive 22 successful launches. Led by Bill Schindler, the Delta rocket earned its industry workhorse moniker for rapidly establishing itself as one of the most reliable and versatile launchers. During the 1960s, Delta launch vehicles paved the way for the burgeoning communications industry, launched America's first weather satellites, and sent probes to explore our universe. AT&T's Telstar 1, the first commercial communication satellite, launched in 1962. And in 1963, SYNCOM 2 became the world's first geosynchronous satellite. TIROS, or Television Infrared Observation Satellites, provided the National Weather Service with man's first view of the Earth's cloud cover. In orbit around the Earth, Moon, and Sun, NASA's Explorer satellites provided us with a deeper understanding of the solar wind, cosmic rays, and Earth's magnetic field and radiation belts. By the end of the decade, launch vehicle modifications, including the addition of solid rocket motors and an upgraded third stage, made it possible for Delta to orbit satellites 10 times larger. The 1970s was an international decade for Delta, as the manifest included scientific and communication satellites for several countries across North America, Europe, and Asia. Perhaps the most demanding challenge of the 1970s was the launch of the Earth Imaging Earth Resources Technology satellite. Later known as Landsat, the mission for the Earth sciences community required major changes to the Delta propulsion and guidance systems. During the 1980s, Delta continued its reliable service to the communications, weather, and Earth imaging communities. But as capable as the Delta rocket proved to be, production came to a halt in the early 80s when national space policy dictated that the space shuttle be used as the U.S.'s primary launcher, signaling the end of the expendable launch vehicle. But in 1987, the Delta team picked up where they left off, and development began on a launch vehicle to support the Air Force's Global Positioning System. On February 14, 1989, Delta 184 began a new chapter in space launch history as it lifted off from Space Launch Complex 17, demonstrating an incredible feat. The Delta II had gone from development to launch in just 2 years. To accommodate the larger GPS satellites, engineers improved the Delta rocket in several ways. The fuel tanks were stretched, a new payload fairing was developed, and larger solid rocket motors were incorporated. The modifications resulted in increased performance and flexibility. By the mid-1990s, the Delta II had delivered the fully operational 24-satellite GPS constellation. And though it was developed for the Air Force, Delta again became a reliable partner to both NASA and its commercial customers.
We have good separation on all 3 airlit solids.
Over the course of its more than 20-year run, the Delta II has launched some of America's best-known scientific and exploration missions.
We have main engine start, 0 and liftoff of the Stardust spacecraft and liftoff of the Delta II rocket carrying the Spirit from Earth to planet Mars.
Liftoff of the Delta II with Grail.
On the commercial side, Delta II launched the Globalstar and Iridium constellations, which brought satellite telephone communication to the world. Continuing its evolution to meet the growing demands of its satellite customers, the Delta team developed the more powerful Delta III. Though short-lived, the Delta III doubled the performance of the Delta II.
So we have ignition and liftoff of the Boeing Delta III rocket.
In partnership with the Air Force's Evolved Expendable Launch Vehicle program, the Delta team began development of the next generation Delta IV rocket in the mid-1990s.
Main engine start.
And we have liftoff of the first Boeing Delta IV rocket carrying the W5 telecommunications satellite for Eutelsat of France.
All Delta IV configurations begin with a common booster core, powered by the RS-68 main engine. Solid rocket motors provide additional thrust at liftoff, and the choice of a 4 or 5 meter diameter payload fairing allows the Delta IV to more precisely accommodate varying payload sizes. The Delta IV Heavy, with its 3 common booster cores, delivers our nation's largest missions to orbit.
Liftoff of the United Launch Alliance Delta IV Heavy rocket carrying the NROL-32 mission for the National Reconnaissance Office.
Delta IV launch vehicles are produced at a 1.5 million square foot state-of-the-art facility in Decatur, Alabama. Processing and launch takes place at Space Launch Complex 37 at Cape Canaveral Air Force Station and Space Launch Complex 6 at Vandenberg Air Force Base in California.
Range safety arm light on.
From its early beginnings as a weapon and deterrent through its transformation into a space launch vehicle, Delta has reliably supported our nation for more than 50 years. Delta's legacy as a workhorse continues today and is a testament to the persistence, dedication, and commitment of an enterprising team that has continually evolved the Delta rocket to support a changing world. And liftoff of the United Launch Alliance Delta IV rocket.
This is Delta Mission Control at T-minus 4 minutes and holding. I'm now joined by John Gadarowski, who last minute has agreed to come in and talk to us about TDRS and their capabilities and why they're important.
So yeah, thanks, Andrea. So the TGS satellite constellation is an important asset because we use that to track the rocket and the spacecraft during ascent and during the vehicle liftoff through the tracking of the vehicle all the way until the spacecraft is separated. So the TDRS constellation is a mandatory coverage of So we just got new word that the TDRS satellite system may be back up and running. So team's still working an issue now. We can maintain our coverage and get the Delta IV ready to fly again soon.
Great, thank you so much, John.
LCR CNET 1.
Go RC.
Yeah, for the teams, SA, the TDRS testing is going to take a little bit longer. It looks like it'll be till 0012 Zulu before they have a full status for us.
Roger, but they are making grounds on potentially getting us the asset we need.
Yes, they're in the middle of transitioning. They've successfully, I believe, transitioned to their SA2 antenna, and they've got a test schedule that should complete at that time.
Roger, just awaiting retest.
Yes, sir.
Thank you for the update.
This is Delta Mission Control at T-minus 4 minutes and holding. A status update from the TDRS network is expected shortly.
Roger, CBC, both LOX and hydrogen.
And second stage hydrogen, the second stage LOX is getting cycled now.
Roger. AC, LC, net 1.
AC on 1.
Yes, properly it is recommending performing valve cycles. I concur with that. Any reaction from you or BSE?
Stand by. LC, this is AC. We agree with the recommendation.
Roger. Field 1, LC, net 1.
Go ahead.
You ready to proceed with foundry and valve cycle test?
Roger.
Proceed. Box 1.
Go.
You ready to proceed?
Ready.
Proceed. And field 2.
Field 2.
You ready to proceed with foundry and valve cycle test?
Ready.
Proceed.
This is Delta Mission Control at T-minus 4 minutes and holding. The launch team is postured to resume the countdown once the tracking network is confirmed ready to support tonight's flight.
LC Field 1.
Go field 1.
Valve cycle test is complete.
Roger.
LC LOX 1.
Go.
Valve cycle test complete.
Roger.
LC Field 2.
Go.
Valve cycle test is complete.
Roger.
LCLD on 1.
Go.
Yes, sir. Please coordinate a new T0 of 00:26.
Roger, 0026.
Good copy.
RC, LC, at 1.
RC in 1.
Please coordinate a new T0 of 00:26:000.
Roger, in work.
ALC, LC net 1.
Go ahead.
Please set the clock for new T0 0026:000.
Roger. LC, ALC.
Go.
Countdown clock has been set with a new T0 of 00:26 Zulu. We're at L minus 10 minutes.
Roger.
LCRC net 1.
Go, RC.
Range is approved. New T0 0026 Zulu.
Roger.
L minus 10 minutes. All communications switch to channel 1. All personnel and visitors remain in present position until launch. Maintain operational silence in the LCC.
LD on.
LD.
MD on 1.
And LC, we have a recommendation due to the delay. We need to adjust the second stage delta P one more time. Value's been recommended by the anomaly team.
Roger. And LC concurs. LD.
LD concurs.
MD.
MD concur.
And that was 4.20, correct?
720.
Roger. And LOX 2, you copy that recommendation?
I copy and it's complete.
Roger. Okay, team.
LCRC net 1.
Go, RC.
Yeah, TDRS is operational and able to support the new T0.
Roger. Okay, team, our new T0 has been coordinated and approved, 0026. And we'll pick up at the status check at L minus 7 minutes.
This is Delta Mission Control at T minus 4 minutes and holding. As you just heard, the TDRS constraint has been cleared. A new launch time of 8:26 p.m. Eastern Time has been identified. This is Delta Mission Control at T minus 4 minutes and holding. The team will pull in less than 1 minute. This is Delta Mission Control at T minus 4 minutes and holding. Let's listen in as Scott Barney performs a final pulling of the launch team.
Status check to proceed with terminal count. First stage systems, propulsion.
Go.
Hydraulics.
Go.
LOX.
Go.
LH2.
Go.
Second stage systems, LOX.
Go.
LH2.
Go.
Electrical systems, airborne.
Go.
Ground.
Go.
Facility.
Go.
RFFTS.
Go.
Flight control.
Go.
COM.
Go.
GCQ.
Go.
Operations support.
Go.
Pneumatics.
Go.
Umbilicals.
Go.
HASGAS.
Go.
ACS.
Go.
Redline monitor.
Go.
Quality.
Go.
Op safety manager.
Go.
ELA safety officer.
Go.
Vehicle system engineer.
Go.
Anomaly chief.
Go.
Range coordinator.
Clear to proceed.
Launch director.
Launch vehicle is ready to launch.
Mission director.
This is EMD. You have permission to launch.
Proceeding with the count.
L minus 6 minutes.
MEQ. Establish swing arm lock pins pulled.
Roger. In work.
The launch team is Polling is complete and the launch team is given a go for launch. The countdown will resume in approximately 2 minutes from now. At T-minus 4 minutes and counting, the team will enter the terminal count and will begin securing the second stage liquid oxygen tank. At T-minus 332, booster liquid hydrogen and liquid oxygen tank securing is started, which includes closing the propellant fill and drain valves. Also at T-minus 332, vehicle transfer from ground facility power to its own internal battery power will be complete. At T-minus 3 minutes, the vehicle ordnance system will be armed and the booster liquid oxygen and liquid hydrogen propellant tanks are verified to be at flight pressure and flight level. At 2 minutes prior to liftoff, the team will verify that the hydraulic system is pressurized, as well as confirm booster, DCSS, flight termination, and battery voltages. At T-minus 120, the team will begin securing the second stage liquid hydrogen tank. At T-minus 60 seconds, the eastern range readiness is verified. At T-minus 50 seconds, the DCSS liquid hydrogen tank is secured at flight level. A final launch vehicle and spacecraft status check is conducted at T-minus 30 seconds. At T-minus 15 seconds, the ROFIs, or sparklers, are ignited to burn off excess hydrogen at the base of the vehicle.
359.
Second stage lock secure at flight level.
5.
Ground pyros in.
The countdown clock is resumed and we are go for launch at 8:26 p.m. Eastern Time.
.307. .249.
FTS internal. CBC locks at flight pressure and flight level.
.2 minutes. 159.
Vehicle internal.
Hydraulic press at without.
155.
CBC LH2 at flight pressure and flight level.
140.
FCS launch and
37.
T-minus 90 seconds. The launch vehicle, payload, ground systems, and Eastern Range are go for launch.
120.
LCU's armed.
FCS count start.
T-minus 1 minute.
Box go.
Rock, report range status.
Range green.
50.
Second stage LH2 secure at flight level.
30.
Status check.
Go Delta.
Go WGS-10.
23.
SRM TVC blowdown.
15.
Rofi ignition.
10.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And we have liftoff of the United Launch Alliance Delta IV rocket carrying the WGS-10 mission for the United States Air Force.
Passing 10 seconds into flight. RSCT chamber pressure looks good. See good chamber pressure across all 4 SRMs. Nice symmetric burn. Now 20 seconds into flight. Continue to see good performance on the RS-68A engine. Now coming up on 30 seconds. 34 seconds into flight. Mach 1 Delta IV is now supersonic. SRM chamber pressure has tailed off from the max pressure as expected. Continue to see good engine performance on the RS-68 engine. Delta is now passing through max Q, maximum dynamic pressure. Now 55 seconds into flight. Continue to see good performance on the RS-68A engine, good performance on all 4 SRMs, nice symmetric burn. Now 1 minute, 5 seconds into flight. About 30 seconds remaining until SRM burnout. Now passing 1 minute, 15 seconds into flight. Continue to see good performance on the main engine. And standing by for SRM burnout shortly. And we have burnout on all 4 SRMs, standing by for jettison. And we have good indication of jettison of all 4 solid rocket motors. Main engine continuing to perform well, chamber pressure looks good. Now passing 1 minute, 50 seconds into flight. Vehicle's gone to closed loop guidance. The Delta IV rocket now weighs just 1/2 of its liftoff weight, burning propellant at a rate of almost 2,000 pounds per second. Now 2 minutes into flight, the second stage ACS system press valve has been opened. System pressure response looks good. And seeing good body rates on the Delta IV as it transitioned to closed loop guidance. Main engine continuing to perform well, engine parameters look good. Now 2 minutes, 18 seconds into flight. Launch vehicle is now 46 miles in altitude, 73 miles downrange distance, traveling at 5,400 miles per hour. Continue to see good performance on the main engine, passing 2 minutes, 35 seconds into flight. And body rates have nulled out now, 2 minutes, 45 seconds in. And the upper stage lock system has begun the boost phase chill down sequence to begin thermal conditioning of the RL-10 engine. Now 2 minutes remaining in the boost phase of flight. And upper stage fuel system has begun boost phase chill down. Standing by for payload fairing jettison. And we have good indication of payload fairing jettison. Approximately 20 seconds remaining until booster begins to throttle down in preparation for BECO, continuing to see good chamber pressure on the RS-68A engine. Now 3 minutes 40 seconds into flight, standing by for booster throttle down momentarily. And boosters now throttling down in preparation for BECO, standing by for BECO. And we have BECO booster engine cutoff, standing by for stage separation. And we have good indication of stage separation. Nozzle extension is deploying. We have pre-start on the RL-10, standing by for ignition. And we have ignition on the RL-10. Chamber pressure looks good, body rates look good. This is the first burn of today's mission. This first burn will last approximately 15 minutes, 15 seconds. Now passing 4 minutes, 30 seconds into flight. RL-10 chamber pressure continues to look good. Body rates seeing a
This is Delta Mission Control at T plus 4 minutes and 48 seconds. We've just heard Patrick Moore report the successful execution of the early events for tonight's flight, and all systems continue to operate nominally. The Delta IV second stage and WGS satellite are traveling over the Atlantic Ocean in a southeasterly direction away from the coast of Florida. The mission is now in the first of 2 planned RL-10 engine burns. This burn will last approximately 15 minutes. Momentarily, we'll hear from Boeing's Tim Maurer to tell us more about the spacecraft. But first, let's take a look at a message from the Boeing team on what it's been like working on the WGS program.
This satellite is providing this capability that provides for the freedom that we have here.
I know that I'm working on something really important. It helps out the warfighter. It makes sure that all of our troops stay connected. It also allows them to stay connected with their families, which I think is really important.
I hope that the people watching this webcast really understand how many hours and how many people had a hand in shaping this very successful program.
My hardware was responsible for controlling the spacecraft.
So I started as the payload system engineering lead on the program. When the program started out, slowly moved in to become the overall payload IPT lead, and then I became the Block 1 program manager.
So I started out as an attitude control subsystem analyst, and I was moved up to be the platform IPT lead.
When your work is important to the military, our country, and the world, you feel better about what you're doing.
There's a feeling like you're doing something good for the country when you're working on a program like that.
So there's a good feeling of helping the military and helping the Department of Defense with something that they have a big need to fulfill.
We're now joined by Boeing's Tim Maurer. Tim, thank you so much for being here.
Thank you, Andrea.
Great. I know I'm really excited to learn more about WGS and what you do specifically. So to go ahead and get started, what I'd like to do first is just get to know a little bit about what you do and your involvement with the WGS program.
Great. So as you mentioned, I work on the ground system for the WGS spacecraft called the Global SATCOM Configuration Control Element. I've worked on this system over various roles since 2003, very near to the initial WGS contract award in 2001. The Army uses the Global SATCOM Configuration Control Element to control the payload. So right now, I'm an integrated product team lead for the Mitigation and Anti-Jam Enhancement Program, or MAGE. MAGE is making changes to the WGS ground system to provide additional enhancements for mitigation and anti-jam for new capabilities for the WGS spacecraft. So as an integrated product team lead, it is my responsibility to ensure that the team focuses on the right priorities to meet our schedule and deliverables. I also work with our customer, the United States Air Force, to ensure that they're fully involved in the process and are satisfied with our approach and progress.
Oh, great. Quite a bit of integration that you do. I can see that. And it's really important that you meet those schedule milestones. So I can really appreciate that. Obviously, it's very important to get those secure communications out. So.
Absolutely.
Great. So now that we know a little bit about what you do and your involvement in the WGS program, I want to learn more about WGS itself. So I'm going to dive into a couple of questions about that.
Certainly.
Sounds great. So how does Boeing design and build secure communications features into the satellite?
So first it starts with the mission. In this case, providing secure, high bandwidth communications for warfighters, ground stations, and vehicles worldwide 24/7. From there, capabilities and requirements are defined and designs created. Next, hardware is built and integrated in our factory back in California, where we test our satellites in environments that exceed what we predict will occur in space. Once that is done, I guess really the question is more not how we do it, but why we do it. As a Boeing employee, this is really more than just a job to me. The products we build serve a greater purpose to protect not only every American, but also our allies. When I walk into work, I know that I'm designing and building the tools that will protect liberty and freedom throughout the world.
That's such an amazing and inspiring message that you just put out there. I think that, you know, in the aerospace industry, especially when we're talking about national security and bringing home our soldiers safe from war, there's no better reason to go to work and do a good job every single day. So thank you for all of the effort that you've done to, you know, work on these WGS satellites and make them be very effective out there, especially on the warfield.
Thank you. It's an absolute honor for me, and I know the rest of the team.
Great. All right, so you did mention a little bit about building and testing. Can you expand on that a little bit?
So most of the satellites that Boeing builds, both government and commercial, come out of our factory back in El Segundo, California. The things that we do to test basically simulate the environment we expect the satellite to be in. Everything from the launch environment, which we just saw with the vibrations and noise, to the space environment with things like radiation and temperature extremes. So in testing, we really have to stress the satellite to put it through its paces that we predict it will be in. So the satellite's payload really is what performs the mission of the satellite. I guess one of our, basically at our factory, we do everything from design, development, manufacturing, integration, and test. So once everything is complete with the integration and test and we've stress tested it, we next move on to making sure that it's ready for launch. Once it's ready for launch, basically it is containerized and shipped to the launch site. So for WGS-10, for example, it moved from our factory to the LAX airport, boarded a Boeing-built C-17 aircraft, and flew here to Florida. So once at its launch destination, it goes through a few more tests before it's finally encapsulated and prepped for launch.
So there's quite a bit of testing that goes on throughout the entire process.
Absolutely.
Amazing. And it's really nice that you have all of those integrated facilities at Boeing. So not only do you do the testing and the development, but you also do transportation and follow the satellite through the entire process.
Full process, yeah.
Yes, and you know, I always think test like you fly. We love to say that all the time. So like you said, we saw a really harsh environment. Yes. We felt it here. We literally felt the floor move. Yep. So it's amazing that these satellites can handle those type of environments.
Definitely.
All right, so we've talked a lot about Boeing and how they build the satellites and things like that, but there's much more than just building. We're going to launch today, and then after the launch, what's next? What does Boeing do to support the WGS constellation?
So WGS is controlled by two different systems on the ground. One is primarily responsible for the platform or flying the satellite. This is keeping it in its designated orbital slot and pointed correctly, as well as changing orbital slots if necessary. The other system is responsible for configuration and monitoring of the payload, so pointing antennas, configuring routes through the channelizer to connect uplinks and downlinks, and a few other configuration parameters. So the payload control system itself was developed by Boeing in parallel with the construction of the WGS satellites. That system is deployed at various sites around the world, and it is what's used to collectively manage the configuration of the WGS fleet. In addition to developing the payload control system, Boeing also supports, through their sustainment services, the day-to-day payload and platform operations of the WGS constellation. So I mentioned MAGE earlier. This is the ground-based anti-jam enhancement that will use existing WGS capabilities to geolocate where interference is coming from and then shape beams to mitigate that interference. So in addition to MAGE, to further improve the security of the communications that our service members use every day, Boeing is working with the Air Force to roll out another ground system in the early 2020s that will enhance protected tactical communications over WGS. So this system is called the Protected Tactical Enterprise Service, or PTES. PTES is a global military satellite communications ground system. PTES will use WGS satellites to allow service members to use the Protected Tactical Waveform, which is one of the U.S. Department of Defense's secure anti-jam waveforms. So we are proud to partner with the Air Force because we know the work that we have done on the WGS satellites really play into a larger system that ensure critical communications for our soldiers and service members so that they are never alone and they always have the information they need to execute their mission.
It's incredible that you say that, and like I said before in a previous question, it really gives you no better job satisfaction knowing that you're able to do things like that. But bringing home people safe and being able to always have that constant communication, I don't think there's anything quite like it.
I absolutely agree.
Yeah, so thank you for that.
Sure.
All right, so I just have one more question for you.
Okay.
Boeing has a robust history, as you know, of building satellites, about 50 years or so between commercial and military type satellites. What is it about WGS that makes it unique?
So WGS is a really interesting looking satellite. One of the most distinguishable features on the satellite are the solar panels. So WGS satellites employ highly efficient space solar cells made by Spectrolab, which is a Boeing subsidiary in California. So on the sides of the satellite are the Ka band antennas. There's also two large polygons on the top, which are the X-band phased array antennas. These polygons hold many different antennas, or horns as we say, and we can phase those antennas together to create beams that we can then point to create our communications. We can also shape those to enable the anti-jam capability. Deep in the cavity of the satellite, behind the radiator panels, is our Generation 6 channelizer. You can think of a channelizer as a computerized switchboard in space that would connect a ship to a commander in the field, for example. So this channelizer, which was also included on WGS 8 and 9, nearly doubles the available bandwidth as compared to earlier WGS satellites.
Wow. Wow, that's incredible.
It really is.
So WGS is very unique, is the answer to that question. Great. So we've learned a lot today about WGS, and you are very knowledgeable on the systems, and I know we very much appreciate your time, but we have another video from Boeing where we're going to go into a little bit more detail on WGS. So let's go ahead and take a look.
Okay.
Virtually every military mission relies on satellite communications. From data gathered by UAVs to teleconferencing between military leaders, WGS is the backbone of our military's ability to communicate. One satellite by itself can't service the entire globe, so it's really important to have an entire network of satellites to make sure that we have full coverage. WGS is the satellite network used by the military and our allies to communicate across the world, anytime, anywhere. We want to protect the satellite as much as we can, so WGS is going through a fleet-wide upgrade right now by uploading new software and modifying the ground segment to allow continuous communications that aren't interfered with. One of the major things that the military has been looking into is how to make satellites more resilient to jamming. Sources of jamming can range from an adversary that's trying to affect your communications path to someone who is accidentally in that bandwidth. One of the enabling technologies for anti-jam capabilities is the use of phased array antennas. By adjusting the power and timing of each of the antenna elements, we're able to create a shapeable beam to avoid the jammer that allows for warfighters to stay connected wherever they're located. When you take into account satellites that allow upgrades through software and the ability to provide anti-jam protection, it all allows us to provide a more resilient system that the military can count on.
And we have MECO, main engine cutoff. Vehicle body rates are recovering nicely from the shutdown transients. And we have begun the thruster activity to correct the body rate dispersions as expected.
As you just heard, we just saw the successful execution of MECO 1. Thank you so much for coming and joining us today and telling us all about WGS. It was great to have you.
Thank you, Andrea. It was my pleasure.
Awesome. Thank you.
Second stage is now turning to the MES 2 attitude as expected. Now 21 minutes.
All right. I am now joined by Sam Wiley. Sam, thank you so much for being here.
Thanks so much for having me. Glad to be here.
Great. I know we have a couple of questions to ask you about WGS, so why don't we go ahead and get started?
Okay, let's do it.
All right. Why don't you start off this interview by telling me a little bit about WGS?
Okay. WGS provides flexible, high-capacity tactical communications to the Air Force, Army, Navy, Marines, Coast Guard, and our international partners. WGS is one program of 6 divisions at the MILSATCOM Systems Directorate at SMC in Los Angeles. The MILSATCOM Directorate develops, acquires, deploys, and sustains space-enabled, war-winning global communications.
It's amazing that we've been able to partner with our allies in such a meaningful way. Can you tell us, you mentioned a little bit about satellite communications. Can you expand on that?
Sure. Generally speaking, radio frequency or RF communications require line of sight to transmit a signal between users. When those two users are over the horizon from one another, a communication satellite must relay that signal. WGS has extremely advanced and innovative technology that enables these communications at extremely high speeds.
Great. So to kind of build on that, can you give us some specific details about WGS-10?
Absolutely. Each and every WGS satellite has more bandwidth and capability than the entire legacy constellation that came before it. Yeah. WGS is the only military satellite communication system that provides simultaneous communications, X-band and Ka-band communications with cross-banding, meaning that 2 users who are on different communication bands can still seamlessly communicate. WGS can also point communication beams and can reposition satellites on orbit, providing unparalleled flexibility to our warfighters and international partners with any contingency that they may have to execute.
Amazing.
With its ground equipment and software updates, WGS has shapeable beams, which allows the satellite to outline a coverage area that eliminates jammer effectiveness. The speed, reliability, and effectiveness of the WGS constellation allow U.S. and international partners the ability to efficiently coordinate in all mission areas, including air, land, and naval warfare.
Wow, that's great. So, as you know, we're currently in the process of launching WGS-10.
Yep.
I know you got to go up to the roof and see it, so that's pretty exciting.
It was awesome to watch.
Yeah, I bet. Can you just tell us what the plan is for WGS after today's launch?
Absolutely. So prior to operational use, the satellite will be positioned in the GEO belt orbit, where it will undergo a series of rigorous tests to ensure that all systems are performing to spec. Once payload performance is validated, the satellite will transition to its operational slot, where our warfighters and international partners will be able to use it.
That's great. So our viewers may not know this, but this is WGS-10 is the last satellite of the Block 2 follow-on contract, which was able to provide much faster communications than previous satellites. What do you think's been the key to all of this success?
So there are multiple keys. The satellites on the Block 2 follow-on contract, WGS-7 to 10, were early forerunners in the streamlining processes, mimicking those used in the commercial industry. On average, delivery times were reduced by 10 months per vehicle without additional cost. These principles will continue to be used for the proposed WGS-11 contract and are vital to the SMC 2.0 initiative, which will make SMC as a whole operate faster, and it will increase or improve the agility of U.S. Air Force space acquisitions altogether.
Incredible. What an incredible satellite and what an incredible day we've seen so far.
Yeah, it's been amazing.
All right, so that's all the questions I have for you right now, but you and I have some really fun stuff to do in just a little bit. So why don't you stick around? Right before stage separation, we're going to go ahead and answer those Twitter questions and get some winners, get some prizes.
I'd love to get some of those prizes.
I know, I want some of those prizes too. All right, for now, we'll get back to launch and we'll see you in just a bit. We have about 4 minutes until main engine start 2. While we wait, let's take a look at my conversation with Brett Bushy, ULA trajectory engineer who I had the opportunity to speak with prior to MST roll. Hi, I'm here today at Space Launch Complex 37 with an engineer from ULA, Brett. Brett, thanks for being here.
Thanks for having me.
As you can see, we're pretty excited because you can see the Delta IV rocket right behind us, and it's a beautiful day. Brett, why don't you start off by telling us about what you do at ULA?
So I currently serve as the Flight Design Certified Responsible Engineer. So I serve as the focal point between the various launch vehicle, hardware and analysis teams and the spacecraft customer as we go through the integration process to come up with a mission design that satisfies not only the spacecraft requirements but also the launch vehicle system and subsystem level requirements. I first started as a trajectory engineer about 29 years ago and progressed through the ranks to actually get this position, and I've been lucky enough to work with a great team of engineers.
What's been your involvement with the WGS program as a whole?
So our group basically takes the inputs from all the various launch vehicle groups and integrates those all into a cohesive trajectory that meets not only the internal launch vehicle requirements but also the spacecraft requirements. So that we go through several different trajectory cycles where we refine the design and improve it, and we basically our team comes out with a final product, and then my job is to review that final product before it goes out the door and sign off on that trajectory design such that that's what gets loaded onto the vehicle and that's what we end up flying. So our group also integrates with a lot of various different organizations to actually make this all happen. So not only do we integrate and interface with the spacecraft customer, we also integrate and interface with the 45th Space Wing to get their approval that our flight plan is acceptable. So it's been great that I've been able to work with a great team of engineers who I've actually seen on a lot of these broadcasts over the years.
In tonight's mission profile, we saw a brief overview of what today's trajectory will look like. Can you expand on that a little bit?
So as you've seen on the broadcast, this mission is typical for an Eastern Range mission where we fly due east when we come off the pad. So we do about a 4-minute burn of the booster, and then we follow that up with about a 15-minute burn of the upper stage, and then go into about a 10-minute park orbit coast. And then we follow that up with a 3-minute burn of the upper stage, and then 4 minutes later we separate the spacecraft into a super-synchronous transfer orbit, which is a little bit different than what a typical geosynchronous transfer orbit is, in that we put it into a higher apogee altitude than what geosynchronous altitude would normally be. And the reason we do this is that actually helps the spacecraft in their propellant utilization and tries to minimize what they actually need to get to their final orbit.
As you know, ULA has launched the previous 9 WGS satellites. Can you provide us with more detail on that history?
So we started about 11 years ago launching the first WGS spacecraft. We launched that on an Atlas V vehicle. In fact, we launched the first 2 WGS satellites on Atlas V vehicles. And WGS was actually designed to be a dual integrated spacecraft, so it can launch on both an Atlas V and a Delta IV. So the last 7 launches will have been on Delta IV launch vehicles. So starting with WGS-3, we launched on a Delta medium 5-4 vehicle configuration. As the Delta IV vehicle evolved and we upgraded the engines, we went back and redesigned the trajectory several different times as we've gone through the various WGS launches, with the last WGS-10 launch culminating in our common avionics upgrades on the Delta IV vehicle.